Right, now that we know what it means for a complex function to be differentiable, it's time to look at a couple of concrete examples. Those examples will mainly be revolving around the exponential function actually, and they will occupy this presentation as the next one and the next one. And well, even though we did a lot of calculus in the previous few presentations, most of what we're going to do here will actually be quite algebraic, and in some ways that might be a good break because the next two shouldn't be as deep as the preceding presentations were. So let's take a look at what we've got. So we want to talk about exponentials and logarithms, and we want to talk about them as functions of a complex variable rather than a real variable. For the exponential function, there will be no surprises because in our investigation of the polar form of complex numbers, we essentially already have introduced the complex exponential. For the logarithm, however, and with it also complex roots, there will be a couple of more subtle things that we have to think about. In some ways, we can predict that already from working with real numbers, because when we take roots of real numbers, we no longer get one answer, we get two, and sometimes we don't get any, of course, and similarly for the logarithm is a single-valued function on the real line, but it is not defined on the negative real line. So there are things that happen for logarithms and roots, such as multiple values as well as places where they're undefined, that just don't happen for the exponential function, which is single-valued and everywhere defined. Okay, so for a complex number z equals x plus iy, we define e to the z to be e to the x times quantity cosine y plus I sine y, and we call it the exponential function. That is exactly the polar form of a complex number. We now just use the input, the radius, and the angle as, or we use the x and y values as radius and angle for the polar form, and so that basically then you could say maps the rectangular representation to something that is polar, if you will. The exponential function turns out to be an entire function, so it's differentiable in the whole complex plane, and the derivative is what we expect it to be from the real line. The derivative of the exponential function is the exponential function itself. To prove that, no surprises there, we look at the real part and the imaginary part of the complex exponential function, and we verify the Cauchy-Riemann equations. Well, du dx, that would be the derivative of e to the x cosine y with respect to x. That's e to the x cosine y, and that is the derivative of v with respect to y, because the derivative of e to the x sine y with respect to y is e to the x cosine y. Similarly, du dy, derivative of e to the x cosine y with respect to y, is e to the x negative sine y, so negative e to the x sine y, and that is the negative of the derivative of v with respect to x, which is negative e to the x sine y. Okay, and that means by the Cauchy-Riemann equations, the function f equals e to the z is differentiable at every z and c. That should be e to the z here. Okay, now it is e to the z. So it's differentiable by the Cauchy-Riemann equations, and, well, we also have that the derivative with respect to z of e to the z is the derivative of the real part with respect to x plus I times the derivative of the imaginary part with respect to x, I times the derivative of the imaginary part with respect to x. That was one bad panel here. I hope we don't have any more problems like that. And those derivatives are e to the x cosine y plus I e to the x sine y. And that, of course, is exactly what e to the z is. And that means the derivative of the exponential function is the exponential function again. Okay, some properties, we know how that goes. There are all sorts of properties that we want that we know the exponential function has on the real line, and so we'd like to have these properties also in the complex plane, and they turn out to also hold. For example, we know how to multiply exponentials. It's by adding exponents. Let's see how that goes with the complex form. Well, e to the z1, if z1 is x1 plus iy1, is z2, and z2 is x2 plus iy2, so just trying to stay with standard notation. X and y are the real parts of z, and corresponding subscripts are assigned. Well, then the product of e to the z1, e to the z2 is e to the x1 cosine y1 plus I sine y1 times e to the x2 cosine y2 plus I sine y2. If we multiply that out, well, we get e to the x1 times e to the x2 out front here. And, well, then we multiply out the parentheses. So we get cosine y1, cosine y2, and that's right here. We get I sine y1 times I sine y2, which is the negative sine y1, y2 here. Then we get cosine y1, I sine y2, that's I cosine y1 sine y2 here, and I sine y1 cosine y2, that's right down here. And if we put that together, we realize, well, the e to the x1, x2, e to the x2 still stays in the front. Cosine y1, cosine y2 minus sine y1, sine y2. From trigonometry, we know that that is cosine y1 plus y2. And if we pull the I out here, we get cosine y1 sine y2 plus sine y1 cosine y2, and that's sine y1 plus y2. And we realize that that's e to the x1 plus x2, because we're dealing just with real numbers here, so that's where we can apply the law, because we know it works for real numbers. And by the definition of e to the I phi, this part here is e to the I y1 plus y2, and that's of course e to the x1 plus x2 plus I y1 plus y2 by the definition of the complex exponential. And then we just sort things out, put corresponding subscripts together, and we get e to the x1 plus iy1 plus x2 plus iy2, and that is e to the z1 plus z2, as we formally, and just formally, knew from the real line, but now we have proved that this also works for complex exponents. E to the z itself is e to the x cosine y plus I sine y. Well, e to the x is never 0, and cosine y and sine y don't have any common zeros, and that means this thing is not equal to 0 for all z and c. And e to the z plus 2 pi I, well, remember that cosine and sine are 2 pi periodic, which means that this is e to the z times e to the 2 pi I, and that's just e to the z, because e to the 2 pi I is 1. That's one full rotation around the origin. Okay, what else do we have? Right, surjectivity of the exponential function. Basically, for every non-zero complex number, there is a complex number so that e to the z is equal to w. That's another result that we sort of know from the real line, because for every positive number on the real line, there is a real number so that e to the x is equal to that number. Well, now the complex exponential function actually reaches all complex numbers except 0. We have to make sure we remember here that this works for non-zero complex numbers. Okay, the proof shouldn't be that bad, because we know the exponential form for non-zero complex numbers, which is that if w is non-zero, then w is r e to the I theta, and that's e to the ln r e to the I theta, because r was greater than 0, and we can use the real logarithm here, and that's e to the ln r plus I theta, and so that means z equals ln r plus I theta is the number we desire, and so that means we can now define a logarithmic function. For z being r e to the I theta being non-zero, we define the multiple valued, and here's where we have to be careful, and that's what will give us some work in the remainder of the presentation, actually. This is a multi-valued function, logarithmic function. We define that as the logarithm of z being ln r plus I times theta times 2 pi n. And that is because, remember, e to the I 2 pi was equal to 1, so e to the I 2 pi n is equal to 1, which means that any values, basically z is r e to the I theta plus 2 pi n as a quantity, and the logarithm wants to recover all the solutions of that equation. So this is similar to when on the real line, for example, you solve a quadratic equation, you take square roots, and you've got a plus minus in there because you want to capture all solutions. In a sense, then, the function that assigns any quadratic equation its solutions is multiple valued where it actually has solutions, because it usually will have two values. This function now is a function that has infinitely many values. That's of course more annoying than just having two values, but in the end it is the same principle. We want these functions to capture all the solutions of the equation e to the z equals w. Okay, so what does that mean now? That still means that this logarithmic function is as much of an inverse of the exponential function as can be, because e to the log z is e to the ln r plus I quantity theta plus 2 pi n. That's e to the ln r, e to the I theta, e to the I 2 pi n. Well, e to the I 2 pi n is 1, so this is r e to the I theta, which is z. So if we stick the logarithm, even as a multiple valued function, into the exponential function, we get the original result back, which is what an inverse should do. However, if we stick an exponential into the logarithm function, well, now we're sticking one value into something that returns infinitely many values. So we're going to get infinitely many values out of this. And we can see here, this is the logarithm of e to the x, e to the iy. Remember, standard idea, z is x plus iy. Well, then we take the logarithm of that as specified up here. So this is ln e to the x plus I y plus 2 pi n, and that's x plus iy plus I 2 pi n. So if we work it out the other way, it still tries to give us back z, but because the logarithm spits out infinitely many values, we will have to contend with this I times 2 pi n, which is sort of like when we solve quadratic equations and we have to contend with the plus minus from the quadratic formula. So that's z plus I times 2 pi n here. Okay. So we have a multiple valued function. Well, we know that from the real line, we typically would like to work with functions that assume only one value. That's why the square root of a real number is defined as the unique positive real number whose square is the number underneath the root. And so similarly, we'd like to define a principal value of the logarithm. And in order to do that, we take a standard representation of z equals r e to the I theta, namely the representation where theta is between negative pi exclusively and pi inclusively, and we define the principal value of the logarithm as capital log of z being ln r plus I theta. Principal values of multiple valued complex functions will typically be noted with the same name but with the corresponding uppercase letter if the function is given as an abbreviation with letters. And well, now let's take a look at that. The logarithm, the multiple valued logarithm of -1, well, that's the logarithm of e to the 0 plus I pi, and that will be 0 plus I pi times 2 pi n. So that's 2n plus 1 pi I. But the principal value of the logarithm is the logarithm of e to the 0 plus I pi, and that should be a capital log here. And now it is a capital log. And that's just pi I because the principal value does not stick the 2 pi n in there. Okay, that leads us to the idea of branches and derivatives. First of all, we want to, of course, be able to differentiate our functions, and on any set of complex numbers, z equals r e to the I theta, so that there is an angle alpha, so that alpha is smaller than theta, which is in turn smaller than alpha plus 2 pi, so we have to exclude some kind of a ray coming off the origin, and r, of course, is still greater than 0. For any set of complex numbers like that, the function log z equals ln r plus I theta. Note that this is not necessarily the principal branch, but because we don't want to introduce too many notations, we denote this thing also with lowercase log. That function is analytic with derivative of the logarithm being 1 over z. Again, the derivative of the natural logarithm on the real line is 1 over x, so it should not be surprising that the derivative of the complex log is 1 over z. And the proof is one of the nicer ones because we've done this as an example when we talked about the Cauchy-Riemann equations in polar coordinates, so that means we don't have to do the proof again. Okay, well, now let's talk about branches. When you've got a multiple valued function f, you want to call a branch of that thing, that you want that to be any single valued function that is analytic in some domain, and at each point z in the domain, the value of capital F is one of the values of lowercase f. So that's exactly the idea that we had for the principal branch of the logarithm. We simply looked at a domain where the function returned single values, and then we proved that on that domain, or on any similar domain, actually the function, the single valued function is differentiable. Okay, as an example, well, yeah, the principal branch of the logarithm on the set where r is greater than 0 and negative pi is smaller than theta is smaller than pi, that is the principal branch of the logarithm, and the terminology is consistent. The principal branch is a branch of the logarithm. A branch cut, and that's something that we're going to have to deal with whenever we have these kinds of multiple valued functions. A branch cut is a line or a curve that we remove from the complex plane so that we can define a branch of a multiple valued function. And so here, for example, we essentially did remove the negative x-axis, right? Because r greater than 0 and theta being negative pi or pi has been removed here, and that's exactly the negative x-axis. So, and then a branch point is a point that is on all branch cuts for a particular function. Well, that should be 0 because the logarithm of 0 remains undefined no matter how I cut. So that means that that one probably will be on all the branch cuts, and that turns out to be the case. So any ray theta equals alpha, for example, is a branch cut for the logarithm. We don't just need the principal branch cut. We could use any kind of ray or any kind of curve that goes from the origin without intersecting itself to infinity. And the point z equals 0 is a branch point for the logarithm because, well, logarithm of 0 is undefined, and it turns out that you always have to go from 0 to infinity in some fashion to achieve a single valued function. Okay, now we've got to be really careful when we deal with branches of multivalued functions, because certain identities will just not work out like they used to. Take the principal value of the logarithm of I cubed. Well, that's the principal value of the logarithm of negative I. And, well, negative I is e to the negative pi halves I, so that is negative pi halves I here as a logarithm, but at the same time, of course, negative pi halves I is not equal to 3 pi halves I. Here's where we have to be careful, because these outputs of the logarithm are actually numbers. They're not angles anymore, and since they're not angles anymore, they're not equal to each other. And, well, the pi halves I, that's the principal value of the logarithm of I, so that's 3 log I. And, well, from the real line, we know that you can take the logarithm of a power by pulling out the exponent, and that doesn't work anymore for the principal branch of the logarithm. Well, so what kinds of identities do we have? Well, for example, whenever we have two complex numbers, z1 and z2, we have that the multiple valued logarithm of z1 times z2 is the multiple valued log of z1 plus the multiple valued log of z2. And that is an equation in the sense that if two of the three values are specified as single values, and that's very important here, then there is a value for the third logarithm so that the identity works out. Let's first prove this in general, and that's where we're going to use the ambiguity. The logarithm of z1, z2, well, that's the logarithm r1 e to the I theta 1, r2 e to the I theta 2. Remember that in polar notation, z is r to the I theta, and we just put corresponding subscripts on the respective variables. Well, then we can put that together. That's the logarithm of r1, r2, e to the I theta 1 plus theta 2. And from the multiple valued logarithms definition, we know that this is ln of r1, r2 plus I theta 1 plus theta 2 plus 2 pi n. And we can puzzle that apart, right? Ln of r1, r2 is ln of r1 plus ln of r2. And 2 pi n is the same as 2 pi k plus 2 pi m as long as k plus m is equal to n. And since n is an arbitrary number, yeah, then we just have arbitrary numbers that have the right addition property here. So this becomes I theta 1 plus 2 pi k plus I theta 2 plus 2 pi m. And that is, the first part here is the logarithm of z1, and the second part is the logarithm of z2. And notice that basically this idea that there is a value for the third one so that the identity works, that basically says whenever two of the values n, k, and m are given, then you can find the third one, because k plus m must be equal to n. So that proves the theorem. And again, we have to be careful here. As an example, 0 is the logarithm of 1, we know that. And 1 is -1 times -1, so it's the logarithm of -1 times -1, which is the logarithm of -1 plus the logarithm of -1. But that's not pi I plus pi I, because that would be 2 pi I, right? And so even though the logarithm of -1 is pi I, and the logarithm of -1 is pi I as a principal value, we get actually that 0 is log of 1, which is log of -1 times -1, which is log of -1 plus log of -1. Since we have a single value here, we should specify a single value here, and it's negative pi I plus pi I, because of course the multiple valued logarithm of -1 also spits out a negative pi I, which is just a pi I rotated by -2 pi back to the negative pi I. Okay, for a complex number, z and n being n integer, not and integer, for these two numbers we have that z to the n is e to the n log x, so pretty much we again apply the logarithm and power laws that we know from the real line, and we get what we expect we should get, but we have to prove it here because we don't know these things for complex numbers. But and then thankfully this identity, unlike the other one, does not have any further qualifications attached. Okay, how do we prove that? Well, we do induction on n. For n equals 1, we've already shown that that works earlier. Well, that's basically the yeah, it's directly from the definition of the logarithm. And for the induction step n to n plus 1, well, z to the n plus 1, typically when you've got something like that, you just split 1 off, and that's what we're doing here. This is z to the n times z, which is e to the n log z, e to the log z. We know that this works for the addition works for the exponential function, so this is e to the n log z plus z, which is e to the n plus 1 log z, which is exactly what we wanted it to be, so that ends that proof here. And so that means if the nth power is gotten by multiplying by n, then z to the 1 over n is e to the 1 over n times log z. That ought to be a root, because if I raise this thing to the nth power, I just get e to the log z, which is equal to z. And this assignment now has n possible values for z equals r e to the I theta, with theta being between 0 and 2 pi, where 2 pi is excluded. Namely, z to the 1 over n is r to the 1 over n e to the I theta over n plus 2 pi k over n, where k goes from 0 to n minus 1, and that's because if you raise this to the nth power, then this part back here becomes 2 pi k if you multiply it with n, and of course, or I 2 pi k, and that of course gives us 1 when you stick it into the exponential function. So that is something new, because on the real line, every positive number had one odd root, and every number had one odd root, and every positive number had two even roots. In the complex plane, every complex number has indistinct roots except for 0, which of course has just 0 itself as root. Okay, so what we're going to define now are complex exponents for a non-zero number, and C complex we define z to the c being e to the c log z. That is a multiple valued function, and this definition is consistent with the definition of real powers for real functions, because ultimately if for real numbers, this definition is consistent with the definition of real powers for real numbers, because even though you can define integer powers by induction and then rational powers via roots, ultimately in order to raise a real number to a real number, you need to use the real exponential function. You need to define it exactly in this fashion, only with c and z being real numbers. So again, it's an extension of something that we know from the real line, and it is also consistent with the definition of integer powers and roots of complex numbers. Now that's something we're not going to talk through all the details, but basically it can be shown that that does work out. Okay, so as an example, let's take 1 plus I to the 4i. Well, that would mean we have to take the logarithm of 1 plus I and stick that into the complex exponential function after we multiply it with 4i, so we get e to the 4i log 1 plus I. That's e to the I 4i log, and 1 plus I, well, the magnitude of 1 plus I is square root of 2, and it sticks out on the diagonal, so the angle is pi over 4. Now we can take the logarithm, so this is e to the 4i ln root 2 plus I pi over 4 plus I 2 pi n. And, well, then we multiply that out. So 4i times pi over 4 is negative pi. 4i times I times 2 pi n is negative 8 pi n. And 4i times ln root 2, that would be, right, root 2 is 2 to the 1 half, so we get 1 half times 4 times ln 2, which is 2 ln 2, and the I comes from here. So that does work out. And notice again that these powers are now have actually infinitely many values, because we're using the multiple valued logarithm function. Okay, so for z not equal 0 and a complex number c, we have that 1 over z to the c, the multiplicative inverse of z to the c is z to the negative c. Again, negative exponents basically denote multiplicative inverses. We knew that already for integer powers, I think, but now we can do it for complex powers, because z to the c times z to the negative c, well, that's e to the c log z times e to the negative c log z, and that's e to the c log z minus c log z, and that's e to the 0th, or e to the 0 plus 2 pi I. Either way, that's equal to 1. And because multiplicative inverses are unique, that means that z to the negative c must be the multiplicative inverse of z to the c. So that's that proof. Also for non-zero complex numbers z and complex exponents c, the principal value of the z to the c is z to the c being e to the c principal value of the logarithm of z. So that also is very consistent and reasonable to get the principal value of the power. We use the principal value of the logarithm. Right, and so you notice again we already saw that here because the logarithm was capitalized. Okay, the principal value function is then of course single valued in its domain, because we're sticking a single value into the exponential function, which is single valued itself. And the domain is, of course, the domain of the principal value of the logarithm, so r is greater than 0, and theta is between negative pi and pi exclusively. And the derivative, well, what should the derivative of z to the c be? The derivative should be c times z to the c minus 1, because we know that's what it is on the real line, so it would be very surprising if that was substantially different, or if there was some kind of a case-based distinction where it's one thing on the real line and a different formula on the complex plane. And in fact, there are deeper theorems that say this just cannot happen. The formulas on the real line must persist. But because we don't have those deeper theorems yet, we have to prove this. And we can because, well, if we take the derivative of z to the c, that's the derivative of e to the c log z. Well, we know how to differentiate the exponential and the principal value of the logarithm because that's e to the c log z. Derivative of the exponential is itself times the derivative of the exponent, which is c times 1 over z, which is c z to the c times 1 over z, which is c times z to the c minus 1. And that's, of course, exactly what we did claim here. And finally, one more word again regarding identities. Even when we are dealing with principal values, we must be really, really careful with identities. For example, here also now for powers. Take a look at I times I raised to the I. Well, we know that that's negative 1 to the I, and negative 1 is e to the I pi, so this is e to the I times pi, and that's e to the negative pi, whereas negative 1 to the I times negative 1 to the I, it's tempting here to just say that that's negative 1 times negative 1 to the I, which negative I times negative I to the I, which is then I to the I. But we can see here negative I is e to the negative I pi over 2, so this becomes e to the I negative I pi over 2, e to the I negative I pi over 2. And I times negative I is negative 1 times negative 1 essentially, and so that gives us e to the pi over 2, e to the pi over 2, and that is e to the pi. And the problem here is that as we are raising complex numbers to these powers, again, things might over-rotate, and as they over-rotate, you can get different values. So be very careful with certain identities, and basically only the identities that we have proved so far should be used as we are working with complex numbers. So it's a double-edged sword. On one hand, a lot of reasonable identities just carry over very easily, and we've seen that in the proofs in this presentation. But at the same time, there are certain entities that, certain identities that we simply have to stay away from, and so that means we can only use what we have proved so far, which is really the philosophy of abstract mathematics to begin with. All right, well, sorry about the various mistakes. I'm going to see if maybe a drink can help me a little bit, and I'll see you in the next presentation. Cheers.